Hi, I'm Andrea, and this is AP Physics C Mechanics FRQs. Today we're going to be talking about 2019 Set 2, Question 2. A toy rocket of mass 0.5 kilograms starts from rest on the ground and is launched upward, experiencing vertical net force. The rocket's upward acceleration A for the first 6 seconds is given by the equation A equals k minus lt squared, where k equals 9 meters per second squared, L equals 0.25 meters per second to the fourth power, and t is a time in seconds. As c equals 6 seconds, fuel is exhausted, and the rocket is under the influence of gravity alone. Assume air resistance and the rocket's changing mass are negligible. Okay, so we're given an equation for A in terms of t, so I immediately think maybe we're going to use a displacement velocity acceleration relationship, and since the rocket is launching into the air and then experiencing only gravity after t equals 6 seconds, I think maybe we're going to use a conservation of energy equation, etc. Alright, part A. Calculate the magnitude of the net impulse exerted on the rocket from t equals 0 to t equals 6 seconds. So this question is clear that we need to find net impulse, and the impulse equation is impulse equals integral force of time dt, or it can equal m times delta v, or delta velocity. So we can use either way. I prefer to use the left side integral of t dt because that's just solving an integral. It's a one-step process. While using m times delta v, you're going to have to find final velocity before you can find net impulse. So let's start with the first option. If you choose to use the integral equation, you must be careful of the limits of integration. So we're given actually the limits of integration from t equals 0 seconds to t equals 6 seconds. So can we write this to 0 to 6 f of t dt? So whenever I see a force equation, I immediately think of breaking it down to mass times acceleration. Since mass isn't changing, we can keep it as a constant coefficient, but we know that acceleration is changing in the 0 to 6 seconds. So we can break down the f of t into keeping the limits of integration, mass times acceleration. But acceleration is changing during this time, and we're actually given the equation for acceleration in the problem. So that fits perfectly. So we can plug this equation into the integral and get 0 to 6 mass times k minus lt squared dt. So we can take the mass out because it's a coefficient, so we get that m times integral 0 to 6 k minus lt squared dt. And then you integrate kt minus L over 3 t cubed with the limits of integration from 0 to 6. So then you get equals m times k6 minus L over 3 times 6 cubed. And since we have the value of m as 0.5 kilograms, we have the value of k and L from the overall problem. We can plug these numbers in to get that an even 18. Since everything is in SI units, we just use the SI units of impulse, which is newtons times seconds, because it's force times time, essentially. And that is your answer for part A. If you choose to use the second option, you have to find initial and final velocity. Question says that the rocket initially starts at rest, so the initial velocity is 0 meters per second. That's easy to find out. Now we need to find the final velocity at t equals 6 seconds. So we can't use any kinematics because acceleration is not constant. But we can use displacement velocity acceleration relationships. So we know that the equation for v of t is the integral of a of t from the relationships. So we can actually find v of 6. So we can actually find the velocity at t equals 6. So we can actually find the velocity when t equals 6 if we just plug in the limits of integration from 0 to 6 of acceleration in terms of t dt. And always and don't forget to write dt or dx or whatever. Don't forget to write dt or dx in any integration you do, because if you don't, it's not calculus and you get docked off points. And you may get docked off points. So with this equation set, you can find that v of 6 equals to... So we actually have the a of t equation given in the question. So v of 6 equals limits of integration still 0 to 6. Plug in the equation k minus t squared dt and integrate. Make sure to show your whole process so that you can maximize the partial credit you get, just in case you get the question wrong. So continue integrating. This is k times 6 minus L over 3 times 6 cubed. This all equals 18, and then the units for impulse is newtons times seconds. And that is your answer for part A. Part B, calculate the speed of the rocket at t equals 6 seconds. Alright, we're calculating speed this time. Since acceleration isn't constant, we can't use kinematics, and if you use the second method in part A, you would already know that we can use the displacement velocity acceleration relationships, or if you're like me, I like to go back to part A's answer and see how that can help me solve part B's answer. So there are two ways of doing this problem. You can either use impulse, or you can use displacement velocity acceleration relationships. This is what popped into my mind first when I was actually doing this AP test. So impulse can either equal the integral of f of t dt, or it can equal mass times delta velocity. So using these two equations, we've actually already found this value from part A. It equals 18 newtons times seconds. We can break down mass times delta velocity into mass times final velocity minus initial velocity. So while we're calculating net impulse, we use the limits of integration from t equals 0 to t equals 6 seconds. So the initial velocity is the velocity of the rocket when t equals 0, and the final velocity of the rocket is when t equals 6. So we know that the rocket initially starts at rest because the question said so. So we know that initial velocity is 0, and we actually know the mass of the rocket from the problem. And with the final velocity as the only variable unsolved, we can then plug in the values from the question to find final velocity. And we get the final velocity equals 36. Since everything is in SI units, it's meters per second. And that is your answer for part B. So you can also use displacement velocity acceleration relationships, and this is essentially the second way to solve part A. So we know the velocity graph can be derived from the acceleration graph because v of t equals integral of a of t. So make sure to pay attention to the limits of integration. To define velocity at t equals 6 seconds, we have to use the limits of integration t equals 0 seconds to t equals 6 seconds for the acceleration integration, because we want to go from start to this point t equals 6 seconds. So you should plug in the equation that you got from the question and integrate. Make sure to keep the limits of integration in mind because those are important to solving the question. We have values of k, we have values of t, so you can plug all the values in to find out that velocity at t equals 6 seconds is 36, and since we're using SI units, it's meters per second. And that is your answer for part B. Alright, part C, 2 parts. Part I, calculate the kinetic energy of the rocket at t equals 6 seconds. So we're just calculating kinetic energy, so I'm just going to use the general equation to find kinetic energy at a point. So the kinetic energy equation on your equation sheet is 1/2 mv squared. We know the mass from the problem, 0.5 kilograms, and we need velocity at t equals 6. And good thing for us, we saw that in part B, so we get 1/2 times 0.5 times 36 squared to get that the kinetic energy of the rocket at t equals 6 seconds equals 324 joules, because joules is the unit for energy. And that is your answer for part CI. Alright, CII. Calculate the change in gravitational potential energy of the rocket Earth system from t equals 0 to t equals 6 seconds. This sounds complicated, the rocket Earth system and stuff, but it's just the change in potential energy of the rocket from t equals 0 to t equals 6 seconds. We can't really use conservation of energy because there's energy lost to the fuel in the rocket, making the rocket go upward. It's upward acceleration, and it's kind of messy. So we're going to use the general equation for potential energy, or in this case, net potential energy. So net potential energy equals to mass times gravity times change in height. So we know the value of mass is 0.5 kilograms. We know the value of g is 9.8 or 10. Either one you choose is fine. And we know that the toy rocket starts from the ground, so we can say that the initial height equals 0. So how do we find the height at t equals 6 seconds? And since there's things launching into the air and we have this acceleration equation, my mind immediately thinks to displacement velocity acceleration relationships. So the equation of h of t is the integral of v of t, and we know that v of t is equal to the integral of a of t. So in order to use this equation, we need to find the general equation of v of t. So v of t is equal to integral of a of t dt. And we're just finding the general equation for v of t, so we're not going to look at specific limits of integration. So if we just integrate the equation k minus l t squared t, we get the equation kt minus L over 3 t cubed plus c. And to find a constant of integration, we just take a point where we know the velocity and the time. So I like to take the initial point of time equals 0, velocity equals 0. So c equals 0 if you plug in its values. So v of t equals kt minus L over 3 t. Alright, now we can use this equation. So I move my work up here. Make sure not to erase any work you actually do in the AP exam, because all steps are important to show your understanding of the concepts so you can get the maximum partial credit in case you do calculation error and plug in wrong numbers into your calculator like I sometimes do. So now we can focus on the displacement equation. So h of t equals integral of v of t. Since we're finding the exact value of the vertical displacement at t equals 6 seconds, we need to use specific limits of integration. So we're going to use the t from 0 seconds to t equals 6 seconds to find the vertical displacement of when t equals 0 to t equals 6. So we can just plug in the equation that we got and integrate once again. So you get that when t equals 6, the vertical height is 135 meters. And remember, we're trying to find change in gravitational potential energy, so this is not our final step. So you got the height at 6 equals 135 meters, and you can plug in into this equation to get that delta potential energy equals 0.5 times, I like to use 9.8 times 135 meters, which equals 661.5. Since we're talking about net energy, the unit is joules. That is your answer for part C double I. Part D, calculate the maximum height reached by the rocket relative to its launching point. So there's multiple ways to do this. My mind immediately goes to conservation of energy because I see maximum height. So that is one way to solve the question. Or because after t equals 6 seconds, the only force exerted on the rocket is force due to gravity, you can also use kinematics to solve the problem. So let's use conservation of energy. So this situation is a bit complex. The rocket has already traveled, we know, a distance of 135 meters, and this is when t equals 6. We know that the rocket then travels some other distance before velocity equals 0 and then falling back down. So looking back at the question, we need to find the maximum height the rocket reaches. So we need to find this distance plus 135. So we're going to make our initial point when t equals 6, and we're going to make our final point wherever this maximum height. But then the question comes, where do we want to indicate as our quote-unquote ground level? So there's two ways to solve this problem. We can either indicate our ground level when t equals 6 and then add 135 meters to the answer, or we can indicate that ground level is down here when t equals 0, so then we don't have to add any additional values to find the maximum height. So let's use displacement equals 0 when t equals 6. So our initial moment is when t equals 6. Conservation of energy says that initial energy equals final energy. So breaking down the energies, we have both potential and kinetic energies in the initial moment and the final moment. If we indicate our ground level when t equals 6, the initial potential energy is 0, and its kinetic energy would be 1/2 mv initial squared. V initial is the velocity when t equals 6, so in the final moment, the rocket would be at a height of, let's just say this is h, so it's mgh plus, since it's the maximum height of the rocket isn't moving up or down, so its velocity is 0. So we know that its kinetic energy is 0. So using this equation, we can cancel out the m's, get 1/2 velocity squared equals gh. We know the value of v from part B. We know the value of g is 9.8 or 10, whichever you prefer. Just keep it constant throughout the test. And we need to find value h. So h is around 66.1 meter, but this isn't our final answer because we want to find the maximum height that the rocket reaches. So we still have to add that 135 meters to the answer to get that h max equals 201.1 meters. You can just write 201 meters. It's around the same, 3 significant digits at least. And that is your answer for part D. Another way to solve this problem using conservation of energy is to indicate that ground level is when time equals 0, which is the actual ground. So the initial moment is when t equals 6, so the potential energy would be m times g times height, which we know as 135 meters, plus its initial kinetic energy, 1/2 mv squared, velocity at time equals 6. And so the final moment is when the rocket is at its maximum height. It has potential energy of mg h max, and at this maximum height point, velocity equals 0, so the kinetic energy equals 0. And now we solve this equation for h max. We can cancel out all the m's, divide g to the side to get h max equals 135 g plus 1/2 v squared over g. You know G to be 9.8 or 10, and V is the velocity when time equals 6. And we actually found this value in part B, which is 36 meters per second. So you can plug all those values in to get that H max equals about 201.1 meters. And that is your answer for part D. So if you like to use kinematics, there is actually a way to use kinematics for this problem. So we know that the rocket has a non-constant acceleration for the first 6 seconds, and we know it travels a distance of 135 meters. But we want to find its maximum height. And we know that during this range of t equals 6 seconds to when the rocket reaches its maximum height, the only force the rocket feels is force due to gravity. So we can use kinematics because A is constant. So we know that A equals gravitational acceleration. We need the initial velocity. We can just say it's velocity when t equals 6 because that is our initial point. We need to find displacement, and we can either use time or final velocity. Since we know when the rocket reaches the maximum height, its velocity is 0, we know that the final velocity of the rocket is 0. So using these 4 variables, we can use the kinematic equation Vf squared equals V initial squared plus 2AD. And keep in mind, this D will only help us find this value D. We still need to add the 135 meters to get the actual answer of maximum height. So plug in the values to get that 0 equals V initial. We found this value in part B, 36 squared plus 2GB. Since we made our positive going downward, the displacement is actually upward, so it's going to be negative. We're going to use the absolute value for that. So it's 36 squared equals 2GD. D is about 66.1 meters. And then so H max is D plus 135, which equals 201.1 meters. And that is your answer for part D. Part E. On the axis below, assuming the upward direction to be positive, sketch a graph of the velocity V of the rocket as a function of time t. From the time the rocket is launched to the time it returns to the ground. T top represents the time the rocket reaches its maximum height, explicitly labeled the maxima with numerical values or algebraic expressions as appropriate. So we have a velocity over time graph. Since we know the equation of A of t, I immediately think, okay, we're going to use some relation of displacement velocity acceleration relationships to figure out how to graph this. So let's start from the initial values that the problem gives us. So the rocket starts at rest, so at t equals 0, velocity equals 0. And we know that when the rocket reaches its maximum height, the velocity is 0. So we can also label that point. Since we know that v of t equals integral of a of t dt, d dt, v of t equals a of t, we know that the value of acceleration is the value of the slope of vt at a point. The question gives us initially the rocket experiences positive acceleration, and then after t equals 6, the rocket only feels acceleration due to gravity, so it's negative acceleration. Since acceleration was first positive and negative, we know that the graph of Vt will be first increasing, then decreasing. So as you notice, the point at which these two intersect, there will be a maximum value. So this maximum value occurs when t equals 6. And we actually have this value because we solved it in part B. So this value is actually 36 meters per second. And we know that this value is after the rocket has launched and before the rocket has reached its maximum height. So let's just label it some point over here. After t equals 6, the acceleration is negative 9.8 or negative 10. Depends on which value you use. So with acceleration as negative 9.8, we know that the velocity over time graph will have a straight line with slope negative 9.8. It's going to have the points from t equals 6 to t equals t top. So we're going to draw a straight line from down there, and we don't know definitively when the rocket reaches the ground, returns to the ground, so we can just keep it like that. So from when t equals 0 to t equals 6, acceleration follows this equation that we're given. And since the velocity equals integral of acceleration, we actually found this equation before. It's v of t equals at minus l over 3t cubed. So we follow this equation for when t equals 0 to t equals 6. So it turns out to be a concave down increasing curve. Make sure the curve connects to both the origin point and the maximum point. And that's all that the question requires. So that's your answer for part E. If you're still confused about how in the world did I find out that, oh, this question needs conservation of energy concept, this question needs kinematics concept, there's a link in the description with my own categorization of each year's questions overall and each component of each question in each year of their concepts. So in the document, each concept can link you to another page where I explain how to identify this concept in a question. I hope that I've helped clarify how to solve this question, and I'll see you in the next explanation video. Bye!